So I hope all of you are doing fine. Let me share my slide. So this week we are going to discuss on tutorial 1 questions. So that's mean that next week will be the test for this course. Okay. I will provide details about the test at the end of tutorial discussion. Okay, so there are 10 questions. Let's go through one by one. I think it's a pretty straightforward question for this course. Okay, first question. Name and describe the 2 types of liquid crystals. So I hope by now you are aware that there are 2 categories of liquid crystal. First, the thermotropic liquid crystal, which refer to a liquid crystal where the phase transition from solid to liquid crystal is due to change of temperature, either by heating or cooling. And the second type is called lytropic liquid crystal, where the liquid crystal phase transition depends on both temperature and concentration of solvent. So question number 2, name and describe the 2 types of thermotropic liquid crystal with respect to the molecular shape of the constituent molecules. So depending on the overall shape of the molecule, okay, we can, I think in this course, okay, we are covering the calorimetric molecule, means that it's rod-like shaped molecule, and also disc-like molecule. So for rod-like molecule, calorimetric, it's a rod shape. So you describe about calorimetric, it's elongated molecule due to the rod shape. And in this case, the anisotropic geometry allows for preferential alignment along one spatial direction. So you can see that the molecular axis is longer than the diameter of the overall of the rod. Okay, and mostly in rod-shaped molecule, it contains a rigid core, like aromatic ring at one side, and then the other side is the flexible hydrocarbon chain. And due to this shape, it tends to form nematic and smectic phases. Whereas for discotic shaped molecule, okay, it's flat like a disc, and the long range orientational order of the disc, it has long range orientation of the disc but no long range translational order. It has different between length, height, breadth and diameter of disc. So you notice that the molecular axis is usually shorter than the diameter for a disc shaped molecule. Again, in terms of molecular structure, most discotic molecule contain rigid core or aromatics at the center of the molecule, and it's being surrounded by a few flexible side chain, so that in overall it gives a disc shape. So due to this shape, it tends to form nematic discotic phase and also columnar discotic phase. Next question number 3. Based on the molecular organization, describe the type of order that exists in the following liquid crystal and at the same time, and then sketch appropriate diagrams to support your answer. For nematic phase, this is liquid crystal phase that has the least order, okay, where the molecules in nematic phase here. Okay, so only have orientation order compared to others, and the preferred direction, okay, of the molecule is most likely to clear drawing to represent nematic phase. Okay, you can just draw a rod-like molecule, okay, that pointed to certain direction and indicate the preferred direction of the director. So note that in nematic there's no position order, okay. No need to draw it such that in a layer. That is for schematic. Okay. For schematic A, question B, okay, part B. In the schematic A, there are both orientation order and positional order. Okay. The positional order gives away the layered structure with a well-defined interlayer spacing. So since it also got positional order, so you can see that the molecules in schematic A are in layered, okay, to satisfy both orientational and positional order. In schematic A phase, the director, okay, the preferred direction for the molecules to point is perpendicular to the layer planes. So this is layer planes, the one that I draw here. So you can see that the director, okay, which is pointed perpendicular to the layer planes. Whereas in schematic C, again, similar to schematic A, it got both orientational and positional order. Okay. However, the director is tilted by an angle with respect to the layer plane. So you can see that here, so that it tilted to certain angle, not 90 degree like schematic A. So that's the difference between schematic A and schematic C. In chiral nematic phase, the molecules only possess orientation order, just like nematic phase. Okay. However, the directed twist around in a helix and the repeated distance along the helix is called pitch. So you can see that it's formed like a helix. Okay. So here, for example, the director pointing this way, and then slowly it start to make a full twist. Okay. So this full twist or helix is called pitch. So this is how you can describe about chiral phase. Next question, question number 4. The order parameter of a nematic liquid crystal is based on the second rank legendary polynomial and usually being expressed as follow. P2, or sometimes we can denote as S to represent order parameter, is equal to the average, okay, of 3 multiplied with cos square beta minus 1 divided by 2. Okay, so sometimes beta is also being replaced as symbol theta just to indicate the angle, okay, between the director and the long molecular axis. So give the definition of for beta and explain why the order parameter is based on the second rank order. So beta or theta is the angle where the liquid crystalline molecules are oriented with respect to the director. In the case of odd rank of legendary polynomial, okay, if we look at the equation, okay, the odd rank will cancel out and hence will always produce a zero value, which is not useful in describing liquid crystal molecules. However, the even rank of the legendary polynomial, okay, they can produce a non-zero for phases with symmetry plane perpendicular to director, like the nematic and schematic phase. So this is all depends on the nature of the equation. So only the even rank can give the non-zero value for phases with symmetry plane perpendicular. And further, you can give example of order parameter. If the value of order parameter is 0, it implies it is in isotropic phase, okay, because the angle is random, right, in its value. If you obtain the order parameter equal to 1, it means that it is completely oriented phase. Okay. Question number 5. Okay, it's related to question number 4. Write short notes about order parameter which can take any value between 0 and 1. So note that order parameter is based on time average structure, where molecules are aligned within a limited range called domain in a parallel or near parallel arrangement described by a simple order parameter S or P2. Okay. The order parameter can be defined as the average of the second length general polynomial. So you can give this order parameter equation in describing order parameter. Okay. It is similar to the previous question, 3/2 cos square theta minus half. Okay, it's just a matter of how you rearrange your equation. So here, theta or beta is the angle between the long axis made with the directed axis and the angular statistical average of quota. So similarly, you can put this condition, the order parameter can take any value between a perfectly oriented system. If the angle is 90 degree, perpendicular alignment, so it will give you order parameter half or negative half. Okay, so actually you can draw a modulus so that your order parameter is half actually. If the molecular orientation are random, like in isotropic phase, theta will take all values. Then if you put it this cos square theta average equal to 1/3, okay, due to random angle, it will give you order parameter equal to 0. Question number 6 on the techniques of identification of liquid crystal phase. Describe briefly the techniques. I think for this course, you have been introduced to 4 main techniques. First, the optical polarizing microscopy. And the differential scanning calorimetry. 4 is the deuterium nuclear magnetic resonance. So write short notes for each techniques. So for optical polarizing microscopy, this technique is based on observation of texture to differentiate the liquid crystalline phases. Okay, the texture observed using polarized light, which result from the defect structure of your liquid crystal sample. So by using optical polarizing microscopy, you can determine the phase transition temperature and also the liquid crystal phase type. As for differential scanning calorimetry, okay, you apply heat to your sample, okay, and you quantify it using this differential scanning calorimetry. It allows you to detect the enthalpy change of phase transition and the transition temperature. It only tells you the magnitude of the, can give some information on the degree of molecular ordering. To change or break down the bond, the order. Okay, that's why the enthalpy will be larger. This is if we apply heating direction. Okay. Nevertheless, DAC is actually a complementary tool for optical polarizing microscopy. So the third technique, X-ray scattering or X-ray diffraction.